Okay, so we're back to the foundations of the aggregate DTC model. I'm picking up where I left off, and we're looking at the Lagrangian. And one thing that occurred to me, I should have said before, is that when we come into the exams and so on, you won't be expected to be able to reproduce this, okay? But it's super useful if you've got a basic idea of what's going on, okay? And I'll explain, there's a couple of key results, or one really key result that comes out of this model that we will be expected to be able to use, and it really helps if you know where that comes from. Okay, so let's have a look again at the Lagrangian, and I'm peering at my screen, see if I'm writing it the same way as in the notes. I think I am. So then we've got minus lambda Ri times this restriction, okay, which is ARIT minus FR of whatever that was times Z RIT, the phi. And then the symmetrical expression here will be ALIT minus FL of that. That's an A, isn't it? Times ZLIT to the phi. So this is firm I's Lagrangian. And the first order conditions for optimal behavior by firm I are, or necessary conditions for optimal behavior by firm I are that the L by the Ri, the L by the Li, the L by the Zri, the L by the Zli must all be zero at the same time as these restrictions hold. And we bear in mind this, okay. But I'm going to shift that down here, and then I'm going to work out the first order conditions and put them up here, and we'll solve the problem. Okay, and it turns out it's not as hard as it looks. I mean, it looks sort of huge, but it's super simple. Okay, so I'm going to pause here and shift things around on the board. Okay, so the first thing we want to do is take first order conditions in Li and Ri. I think that's what it says in the notes. Yeah, okay. So what do we get? The L, let me just check that's visible. Yeah, the L by the Li must be naught. What is that? So first we go here. What is the Yi by the Li? Now then, differentiating this with respect to something in here, you need to be able to do this. Okay, this is super important. Okay, so I'm going to do this once here, very slowly and carefully. So this is your reference point. Okay, it's, what do we call this? The chain rule, I think, or is it the product rule? Whatever. We start by differentiating the outside. So we go 1 over epsilon times the square bracketed term to the power of one over epsilon minus 1. Okay. Then we go inside and we say, if we think of this as Li to the epsilon, we've got epsilon times Li to the epsilon over Li times Ali to the epsilon. So it works out as epsilon times ALI Li to the epsilon over Li. Okay, so it's much easier in the continuation if you keep this term together as it is. And to get the -1 on this, you divide through. Okay. But that's basically that. We're going to have a look at this term in a minute, but let me finish here first. Where else do we have Li's here? It's just here, isn't it? So we end up with a minus WL. Okay. Next thing to notice is that if we put a colon here, then we can wipe this equals 0, and we can put equals WL there instead. Next thing to notice is we can bring this Li up here, can't we? We multiply both sides by Li. So then we have this, which is a lot simpler. Okay. So that is the first order condition so far. But now we've got epsilon and a 1 minus epsilon. So we can wipe those. The thing is, you're going to be doing this a lot, okay? This kind of differentiation. And once you get used to it, you can just write this down, okay? But don't just write it down unless you're confident. If you're not confident, do it in several steps, yeah. And then if you do it in several steps a few times, you'll start to see the patterns in your head and you'll just be able to write this down. Because the next thing is, what's this? We can write this as 1 over epsilon minus epsilon over epsilon, can't we? 1 over epsilon minus epsilon over epsilon. That's the same as 1 minus epsilon over epsilon. So we can write this as the stuff in the square brackets to the power of 1 minus epsilon over epsilon. Okay. But there's more. Okay, we can do more to simplify this. Because, okay, I'm right on the border of what's visible here, sorry. Hopefully this comes out on the recording. Let me shift it down a bit just in case. So we've got the square bracket term, the 1 minus epsilon over epsilon times the rest. Okay. We can rewrite this as the square bracket term to the 1 over epsilon to the power of 1 minus epsilon. Okay. So that should be straightforward, I hope. The square bracket thing to the 1 minus epsilon over epsilon is the same as this, yeah. If you just take a trivial example, 2 to the 3 times 2 is the same as 2 cubed squared, yeah. 2 to the 6 is 2 cubed squared. This is the same step I made here, isn't it? Okay. But what's the thing inside the curly brackets? It's just yi. Okay. It's just yi. We can wipe this whole thing and say, look, it's just yi to the 1 minus epsilon. ALI to the epsilon equals WL LI. That is the first order condition once we simplified it. And once you've got the hang of this, you can write that down straight away. Okay. You know that, okay, this 1 over epsilon here, that's going to cancel with that epsilon. You know that this is to the power of 1 over epsilon minus 1, which is 1 minus epsilon over epsilon which is y to the 1 minus epsilon, times AL Li to the epsilon over Li, bring the Li up, WLi, you're there. Okay. Once you've done this a few times, you will start hopefully to see your way all the way to this answer without writing anything else down. By symmetry, I love symmetry. Okay. Don't be afraid to use symmetry. Okay. There's a symmetry here, which means that we can just write down dl by the Ri. These Li's and Ri's are kind of interchangeable everywhere. So dl by the Ri must look essentially the same. We're going to end up with this. Okay. And then if we divide this equation by this one, we end up with, I'm going to switch sides here. We're going to end up with WL Li over WR Ri equals ALI Li over ARI Ri to the epsilon, which is our result. And I hope if I skip to the next slide, that's what, I can't see it, but I think that's what it says. Okay, so I'm going to pause the video. I'm going to park this result in the corner somewhere, and then we're going to look at the next result. Okie doke. So that is the result of the first order conditions in Li and Ri. What about the first order conditions in, let me think. Right, yeah, I didn't say this before. We need to take first order conditions in ALI and ARI. Okay, these are variables too, aren't they? They're changing over time, and in the Lagrangian, therefore, when we're doing the Lagrangian method, we need to take first order conditions in those too, because they're changing over time. Okay, but here, to get these, I'm going to push you a bit in terms of your thinking, and I'm going to say, look, we can just use symmetry. We don't need to do anything more than just note the symmetry. Imagine just wherever there's an ALI, write Li, and whenever there's an Li, write ALI. Nothing happens, nothing changes here, right? And the same thing here if we switch ARI and RI here. But also here, if we switch ARI, so yeah, we should have T's everywhere really. If we switch, corresponds to lambda R. This is the price, this is the quantity. Okay. And WLI corresponds to lambda L. So it turns out if you think carefully about the symmetry, we can just write down the answer to these first order conditions. Wherever there's a WL, we put a lambda L or a lambda Li. Now this lambda is specific to that term, isn't it? Wherever there's an Li, we put ALI. Wherever there's a WR, we put a lambda RI. Wherever there's an RI, we put an ARI. Wherever there's an ALI, we put an LI. Wherever there's an LI, we put an ALI. So that nothing changes on this side and the same here. Okay, so that's it. Those are the two first order conditions once we've simplified. We don't actually need to do any work. if we can see that symmetry. And of course, if you don't believe me, or if that feels too scary or tricky or whatever, you can do it. You can go through everything and you'll get this. Yeah, okay. Right, I'm going to pause again here. Okay, so let me flick over the slide. First order condition in ARI and ALI, or whatever it says, and we get the symmetric expression. Now, what does it say? Well, I can't read it, but I guess it says take first order conditions in the last two variables, ZRI and ZLI. The L by the ZLI, for instance. The necessary condition for an internal optimum is that that is naught. And what does this look like? So, relief, no Z's in here, so we don't need to differentiate this time. We've just got here minus WZ. And then we've got here, we've got minus plus. Oh, we're on the L's, sorry, here. Minus is plus, lambda L, FL of A, and then this. So it's 5 times lambda Li, FL of A, ZLIT to the 5 over ZLI. So it's plus 5 lambda Li, FL, ZLI to the 5, and I draw the T's everywhere. It's more consistent. Divided by ZLI. Why don't I put the -1 up here, because we're going to end up bringing this over. Yeah. So again, I'm going to save ink by switching this to a colon and saying that implies that WZ equals that. And then I'm going to bring this up here and we can say WZ ZLI equals that. Okie doke. Am I recording here? Yes, I am. By the way, sorry about the horrible sound quality on the first video. I hope that's sorted now. Yeah, and then again, as I hope you can see by now, or from the previous time, there's symmetry again here. The corresponding expression in R is going to be WZ, ZRI is phi, lambda RI, FR, ZRI to the phi. When we divide these two, one by the other, we get WZs are going to go out. So we get ZLI over ZRI, phi's go out. The FL, oh yeah, and then we get lambda Li, FL, ZLI to the phi over lambda Ri, FR, ZRI to the phi. This looks a bit messy, but then we notice, wait, FL, A, ZLI to the phi, that's just ALI. And this is just ARI. And suddenly, we've got that. And this is seriously good news. Yeah, this is fantastic news. Because look at this. This is unbelievable news because look, This is saying relative investments in the two types of knowledge are given equal to this. But this is equal to this. And this is equal to that. So we put this chain of three results all together. What do we get? Pause the video and have a think. Okay. While you're thinking and pausing, I'm going to rub off and then I'm going to write up the answer. Okay, so the answer is that this is equal to this. ZLI over ZRI is equal to WLLI over WRRI. What does this mean? This is relative investments in the two types of knowledge, and this is the factor shares. Okay, so this is like a beautiful result. Yeah. It's saying if a firm is spending 10 times more on hiring labor than it is on buying the resource, it'll invest 10 times more in trying to make its labor more efficient by raising AL than it will in trying to make its resource use more efficient by raising AR, which is exactly what Solow says should happen intuitively in his 1973 paper, but he doesn't do the math because he hasn't got those modeling tools at that point. So this is a way, using this, we can basically model how an economy develops over time. Okay, because what is changing, typically in our models, we're going to say, okay, there's some supply of different inputs, and that's sort of determined exogenously. And then what happens over time, given that supply, what happens to the knowledge stocks? And then we might introduce an exogenous shock to supply of some input, like, you know, suddenly more trees start washing up on the beach. What happens? How does the economy adapt over time? And we know in the short run, if epsilon is negative, if suddenly fewer trees start washing up, the factor share of trees is going to go up. So we've got a market for trees. Okay. The people are going, yeah, I should have said that. We're assuming the whole time there's perfect markets. So people are going to the beach and then they're trading trees, right? So there's a market for the trees and they're going to command a high price. If fewer trees start washing up, their price is going to go up a lot. The share of trees in firms' production functions is going to go up. But then over time, firms will invest in improving their tree using knowledge, and the share of trees will go back down. This is basically what's going to happen in these models. Oh, but wait. Hang on. So I've oversimplified here, haven't I? I've already run it off. But we should have had, no, we shouldn't. No, this is cool. Yeah, this is cool. Sorry, as you were. Okay. Then in the notes, let me see. Okay. So how does this then play out in the aggregate when we try to put an overall general equilibrium long run model together? That's what we're going to look at now. So I guess what I'm going to do is wipe this board. Well, we'll leave that result, which is our key result, and we'll set up the model here. I'm going to pause while I clean up the board and do that. Okay, so how do we now put this back into the overall economy context. So I've drawn a very rough version of the picture on the slide here, the aggregate model. So now instead of one firm, we're thinking of all the firms, lots of different firms, or a continuum of firms. We've got the total quantity of labor, the total quantity of research labor split between the two sectors. We've got the total quantity of resource coming in, which is the sum of the quantities to each of the firms. And it's made using final product. And what doesn't, of the final product that doesn't go here, that goes to consumption. So when we aggregate across all the firms, we end up with big Z L over big Z R is equal to WL big L over WR big R, which is equal to, I brought up that result as well from down here, AL L over AR R, the epsilon, where these are the overall general knowledge levels, which are the sum of all the knowledge levels for each of the firms. So this is what happens in the aggregate. So if the share of labor is big, we get more, or if the share of labor goes up compared to resources, we get more investment in labor augmenting knowledge, AL. So AL goes up, because epsilon is negative, that means the share of labor goes back down. So we can see that there's likely to be a tendency for stability here. If there's a shock that pushes the share up in the short run, in the long run, the share is going to go back down. But how powerful is that mechanism? It depends on exactly how knowledge is made. So what have we got here? We've got ALT is ALT minus 1 over zeta L. Times ZLT to the 5. This is at the aggregate level, but we could have also had it at the firm level. So this wiggly thing is zeta. Okay. And symmetrically, we've got ART is ART minus 1 over zeta R times ZRT to the 5. So when we divide one by the other, we get ALT over ART is equal to ALT minus 1 over ART minus 1 times zeta R over zeta L ZLT over ZRT. Okay, so in balanced growth, if these quantities are staying the same, this is a particular case actually, there's a more general proof for prices, which is a little bit more tricky. I'm not going to take you through that here. I think we do that in one of the problems. But let's just think, and I might even sort of be doing that in the slide, but I think I'm going through that in the slides, but I'm going to go away from what I do in the slides here actually. Basically, I just want to say, in the simplest balanced growth path, when L and R are constant, then for balanced growth, we want ALT over ALT minus 1, the ratio of the growth rate in ALT to the growth rate in ART, that needs to be 1. They need to grow at equal rates if it's going to be balanced. If these are constant or growing at equal rates. For balance then, L and R are constant, AL and AR needs to be growing at equal rates, which means we need a unique ratio of ZL to ZR, which means we need a particular ratio of factor shares. Okay, so there's some particular ratio of factor shares that gives balanced growth, whatever the values of L and R. If L is too big, what happens? If L is too big, then epsilon is negative. So the share, this is the share, yeah, when L goes up, epsilon is negative, so this goes down. So the share of L, because L's on top here, goes down. Investment in L augmenting knowledge goes down. So when L is too big, its share is too small, ZL will go down compared to ZR, AL will go down compared to AR, and the effective quantity of L will go down and will move towards the steady state or the balanced growth state when we're at the right share. Okay, so there's a unique factor share, but ratio of factor shares for L and R that gives stability. And what I show in the slides, which I'm not going to go through, is that we can make the same argument even if L is growing at a constant rate compared to R, or if R is growing at a constant rate compared to L. Or indeed, if WR is constant, remember in the data we see that WR is constant and WL grows at a constant rate. If we assume that that is happening exogenously, we can also show that that leads to, that is consistent with a balanced growth path, or the economy. If WR is constant and WL is growing exogenously at a constant rate, we can show in that case, again, that the economy will converge to a balanced growth path with a fixed share of labor compared to resources. And again, if there are shocks, it'll tend to come back to that path. So, where has this got us? As I'm skipping this slide basically, but the last line, the BGP is stable as long as epsilon is less than 0. And then we have this picture, the next slide, just illustrating this idea that if some shock forces the ball away from the bottom of the valley, it's going to head back there over time. Okay. So on balanced growth, ALL, well, that's wrong, isn't it? Well, yeah, ALL over ARR is constant. WLL over WRR is also constant. The factor shares are constant. That's exactly what we see in Cobb-Douglas. So this model, remember what was the problem with Cobb-Douglas? It fitted the data. Remember this data? Time, log, y, r, wr. Cobb-Douglas fits that data. But we said, yeah, but why? What's really going on? This could be an explanation for what's really going on. Okay, in the short run, yes, we have, oh, it's gone, but we have this CES function. And if inputs of one of the, or quantities of one of the inputs falls, its price will rise dramatically and its share will go up. But then over time, we'll see investment in the knowledge augmenting that factor and its share goes back down. It's just so beautiful. Okay, isn't it beautiful? But there's a problem. there's a problem. I hate to say this, but there's a horrible, horrible problem. What's the problem? Let me just check how many slides I've got left. I've got 2 slides left. Yeah. What is the problem? The model predicts that if WR is constant while WL increases, then AR over AL should decline. So the model, okay, I'm going to pause and clean up here and redo this diagram. Okay, so here's my redone diagram. Log scale here, time here. And remember, the only thing, the levels of these curves don't mean anything. They're normalized. It's the slopes that's important. WR is constant, the price of the resource input. Of course, in reality, we know it goes up and down, but the overall trend. And we're assuming labor is constant. Yeah, we're not interested in population growth. If we added it, it doesn't change anything in principle. Okay. So that's WR and L. And here we have GDP and resource use like this. This is what we see very roughly in the long run global data. According to this model, what should we then see in the global productivity data? We should see that AR tracks Y and R. Sorry, no, AL. Whoa, whoa, whoa. Labor productivity grows with Y. That is fundamentally driving growth. But because, oh, and we should have had the data, sorry, let me start again a little bit. WRL here, WLR here, and Y. That is the data. Okay, this is the wage is growing at the same rate, or this is payments to labor and capital, if you like. We'll call it the wage, but it's labor capital together, really. But we'll call it the wage, GDP, and resource use are growing together here, and the resource price and labor inputs, physical labor inputs, are here. Then what does this model tell us about AR and AL? It tells us that AL should be growing like these guys, and AR should be growing like these ones, flat. Because WR doesn't go up, AR doesn't go up either. Which means either in the limit, we shouldn't bother investing at all in raising AR, or if we add some depreciation of knowledge into this, we can get a low level of investment to make this make a bit more sense. Okay, but what does the data say about AL and AR? Because this is kind of odd, isn't it? We're not getting any more efficient at using resources. We're getting way more efficient at using labor, but we're not getting any more efficient at using resources. So is this really the case? So if we think of like metals, coal, oil, gas, this is saying we're not getting any more value per ton of metal or per ton of coal, oil, and gas today compared to what we were doing 100, 150 years ago. This is super weird, isn't it? This is incredible. I don't know if you've heard of decoupling, but this is all about decoupling. It's like the GDP, real dollars, it's not about inflation, real dollars of GDP per barrel of oil are the same today as they were 100, 150 years ago, more or less. This is shocking, isn't it? This is totally shocking. We haven't raised AR in aggregate. But according to this model, that means we haven't raised AR at the level of individual products either. But we know that that is completely wrong. Like if we think about a car today compared to a car from the 1920s or 30s, if we think of electricity generation today compared to electricity generation in the 20s or 30s, if we think of a light bulb today, or you can see the reflection from one there, compared to a light bulb in the 20s or 30s, how much more useful product are we getting out from a given input today compared to 100 years ago? Well, it depends on the sector, but it could be anything from about 20 times more to 100 times more, or even 1,000 times more. The efficiency with which we can use resource inputs, especially energy inputs, has gone up massively. And what we can do with metals has also improved massively. We can use metals far more efficiently today to make far more amazing stuff, more valuable stuff from a given quantity of metal. But for some reason, that doesn't show up on the aggregate. But my point is that this model is failing to explain the data, because according to this model, the problem is a failure of resource efficiency to increase. But when at the product level, okay, remember we've got, in this model, we've got a bunch of firms, each of which has its own product, and each firm in equilibrium fails to raise its resource efficiency because the resource price isn't going up. The price of labor, capital is. And this failure to raise the resource efficiency at the product level translates to the aggregate level. But when we look at reality, we see that at the product level, looking at light bulbs, cars, etc., efficiency has increased amazingly. But somehow this doesn't seem to be reflected in the aggregate level. So we need to go back to the drawing board to try to understand why that is and what's going on. Let me just check the slides. Yeah. And the final slide then. So if this model is failing to capture the data, what's wrong with the model? Yeah. What's the key assumption from the model that didn't make sense? Because if the model isn't reflected in reality, then it's like we need to look at the model again and like, okay, what went wrong? You know, this looks so great and it was so beautiful. What went wrong is this. This is where we went wrong. What we assumed here is that new knowledge, labor augmenting knowledge, builds on existing labor augmenting knowledge. And then inputs, research inputs. A new resource augmenting knowledge builds on existing resource augmenting knowledge. Plus, then we need to put in research input. In reality, it's different, right? So, in reality, if I want to improve the way that I can make use of coal or solar energy or wind or whatever, I don't just look at existing coal technologies. I look at the whole range of technologies available, okay? Maybe in this sector, the overall economy, which is far bigger than this sector, maybe we developed computers, okay? Maybe we developed much stronger, better ways of building pylons instead of out of wood if we want to make a windmill. 100 years ago, we used cloth and wood to make a windmill, cloth sails and wooden constructions, yeah. 100 years later, we're using metals. We're using propellers that were developed in the aircraft and boat industry. We're using metals developed in the rest of the economy. We're using electric motors developed independent of the wind sector, etc., etc., etc. So productivity in this sector is borrowing massively from discoveries in this much bigger sector, the overall economy. Massively, okay. Which means that this gets pulled along with this. So that explains what's wrong with this model. But then we're still left struggling to explain why then does the factor shares stay the same? Why doesn't the factor share of resources drop when the price of resources fails to rise and AR keeps rising? Resource productivity rises because it's pulled along with labor productivity by spillovers. The price of resources doesn't rise, surely then the resource share should fall. Why doesn't it? Dun, dun, dun. Well, wait for the next exciting installment because that's the next lecture, I guess. It's not this lecture anyway. So see you soon.